let's now attempt to apply Stokes' theorem. And so over here we have this little diagram, and we have this path that we're calling C. And it's the intersection of the plane y plus z is equal to 2. So that's the plane that kind of slants down like that. It's the intersection of that plane and the cylinder. Actually, I shouldn't even call it a cylinder, because if you just have x squared plus y squared is equal to 1, it would essentially be like a pole, an infinite pole that keeps going up forever and keeps going down forever. So it would never have a top or a bottom. But we've sliced that pole with y plus z is equal to 2 to get, and where they intersect, we get our path C. We also have this vector field defined in this way, and we're asked to evaluate the line integral of f dot dr over this path with this orientation. And we could directly solve this line integral. We've done it before, and actually we'll do it again to show that we're getting the same answer. But this is about Stokes' theorem. So let's see if we can apply Stokes' theorem to this circumstance. So Stokes' theorem tells us that this is going to be the same thing as the surface integral over a piecewise smooth surface bounded by this boundary right over here. And actually, we'll pick the simplest of all of the surfaces bounded by this. I'll pick the portion of the plane that is bounded by C. So S is going to be the portion of the plane y plus z is equal to 2 bounded by C. So it's going to be the surface integral over this. We could have picked any other surface too that's piecewise smooth bounded by this, but this is going to be the easiest for us to work with. We have information on it. It's a nice flat, it's at an incline, but it's a nice flat surface that we're going to be able to operate on analytically. And so we're going to take the surface integral of the curl of our vector field dotted with, and we could say dot ds if we think of the vector differential, or we could say dotted with the normal vector at any point, ds, times the little section of our surface, a little surface differential right over there. And we've talked already about orientation, so we want to make sure that we get our orientation right. We are traversing it in this direction, and if we think about the little man analogy, when he's walking in this direction, if he's walking with his head upwards, then the surface will be to his left, and so we want the normal vector that would also go upwards. So the normal vector would need to go, the unit normal vector would need to look something like that. The other analogy, if you're twisting a bottle cap like this, then the bottle cap will move in that direction, in the direction of this normal vector. So we've set it all up. Now all we have to do is evaluate this integral. And to evaluate it, we have to do a couple of things. We, one, have to come up with a parameterization for our surface, which shouldn't be too difficult. We've done it before when we evaluated surface integrals. And we also have to calculate what the curl of f is going to be. And then we just need to evaluate the double integral after all of that. So I'll do that in the next few videos.